DSM papers that it was citing, referring to. Since 2001, there have been over 1,000 additional DSM papers. So a lot of people have started to do work in this area. Over 500 journal papers alone on DSM or talking about DSM at some level. And so there's a lot of stuff out there. And so this paper was not a review because it didn't have space to go into detail about what each of these papers had done. It was less ambitious than that. It was a high-level survey, kind of what's the landscape look like now. And so some of these ideas I'm going to talk about came from that survey. And looking at that big picture, what stood out, where were the valleys as well, meaning some gaps and some opportunities. So I put in one slide since the tutorial is later. And this is just in case anyone here needs basic DSM orientation. But many people find it easy to understand what we call a node link diagram or a network diagram or a directed graph diagram. And it can be shown in an equivalent DSM square matrix. So some key basics about DSM: it's always a square matrix, same number of rows and columns. And the nodes or elements in this network, think of these shaded cells along the diagonal as representing them, and then think of the cells off of the diagonal as capturing the presence of a relationship. And sometimes with different numbers or symbols, we say more than just presence. Maybe we say strength or frequency or importance, things like that. So the two ways of looking at the same thing at this point. But the one on the right, as you start getting more and more nodes and more relationships that you want to document, it looks like a nice plate of spaghetti and meatballs at an Italian restaurant. And it's hard to see patterns sometimes. Yes, sometimes we can cluster and color these nodes in a graph and see interesting things as well. But the DSM just has some visual advantages for seeing the system and also seeing patterns within the architecture. So that's some of the big benefits of DSM. Most of the analyses that we talk about, you can do in either representation. It's really math behind the scenes going on. But again, the matrix sometimes is helpful for seeing the result of that analysis in a clear way. So DSM is not the hammer for every nail. There are other useful tools out there. DSM is one good tool to have in your toolkit if you are an engineer or a manager and you want to know when to take it out and use it, when it's most useful. So just for fun, I found this several years ago. I think a Slovakian guy created this matrix, and he doesn't call it a DSM, but it really is a DSM. And this is how people in science see each other. And so we have undergraduate students, PhD students, postdocs, professors, and technicians. And how do undergraduates see themselves would be the top left one. That's the Einstein picture. How do the undergraduates see the PhD students, and so on. How do the PhD students see the undergraduates? That's here, the toddlers. So you can stare at this for a while. Each picture has some sort of laugh connected with it. And apparently this was pretty popular on the internet for a while, went viral. A lot of people forwarding it to each other. And I don't know how old it is, but it's several years old. But it's an example of a DSM put to kind of an unusual application. So who knows how many possibilities there are for DSM out there, even things that could go viral. It takes a while to look at this and appreciate it, but we'll move on for now. Maybe we'll come back later. So in this presentation and in the accompanying survey paper, it looked at some traditional DSM application areas that most people who've come to this conference before are very familiar with: product, organization, and process DSM applications. There's also some additional DSM applications, and I was delighted to see the Bosch presentation earlier, which was looking at relationships among tools that are used in development. And so that's not something you see too often with DSM, but I think it's very interesting. And another interesting area like it is requirements or goals of a system or a project. These could also be related, and yet we don't see many applications of those. So I'm going to say a little more about those later, but there's some other potential applications. And then, of course, domain mapping matrices, multi-domain matrices. These have a lot of potential, and we've started to see more of those in many DSM conference papers than even just traditional DSMs. So those have really shown lots of recent application interest. And then I want to talk not just about types of DSMs, but how do we build DSMs, meaning how do we get the information that goes into them? Sometimes that's easy, sometimes it's very difficult. So just building DSMs is a challenge in many cases. And then how do we show the DSM? You know, it's a square matrix, but after that, you see many different ways of coloring, sizing, symbolizing within DSM applications. And so what other opportunities might there be there? Analyzing DSMs, we've got clustering, we've got sequencing. These need some further definition and improvement, I think, but what other analyses might also be interesting? And then where could we use and apply DSMs? So I think there's opportunities in each of these different aspects, and I'll mention several of those. So let's start with building DSMs. How do we do that? One of the big challenges that's been around for a while, it's not just a DSM challenge, it's a modeling challenge, but we've noticed, especially with DSMs, that different modelers build different models. So if I go to you and ask you to build a product DSM representing some product or system, something simple in mechanical engineering, you see toasters, cameras, power tools, things like this modeled with DSMs. You start to see more sophisticated products like copy machines, and then eventually automobiles, spacecraft, aircraft, ships, many complex products. And yet, when you build a product DSM like that, how do you know that you've got the right set of components and relationships? And if I asked each of you to build a model of the same product, all those DSMs may not look the same. You might make different choices about decomposing systems into subsystems, into smaller components. And then you might make different choices about how far to decompose. Do you stop with 10 major subsystems and build a 10 by 10 DSM, or do you build a 1,000 by 1,000 DSM of much, much smaller granular components? These are modeling choices that get made. And the question is, how do we make those choices? Is there some systematic way to do it? Usually it depends on what purpose you have. What questions are you trying to answer with your model? But if that's true, and it is true, then that means a model built for one purpose may not be able to answer other questions when you have another purpose. But in industry, I saw all the time, people would build a model to answer one or two key questions, support a few decisions, and then they thought that they, quote, had a model of that system or whatever it was, and that they could then use that model to answer all sorts of other questions, which sometimes yes, but sometimes no. Sometimes this was misleading or confusing. And so how we build the DSM, what it can and can't do depending on how it's built. These are important questions to answer and important to clarify for people who want to use DSMs. This is really true for any complex system model, but I think DSM, if it's going to get past some roadblocks and become one of the dominant complex system models, if it could be one of the first to help answer these types of questions, that would be helpful. Another challenge, different models yield different metrics. So if you've seen many DSM papers or cases, you may have seen that often people will try to take a DSM model and measure something in it, like amount of modularity or in degree, out degree of the components. How many inputs or outputs do they have, that sorts of thing. But of course, all that depends on these decisions we've made up front about how many components and relationships we've captured in the model. And so if we're going to use metrics like this, we have to realize the limitations of where they came from. And so modularity is actually very difficult to measure, not so easy to know. There's kind of a scale of more or less modular, but it's very unclear what the extremes are in some cases, and especially the middle points along the scale. So be careful using a DSM model, calculating some metric from it and saying that's it. Sometimes it's useful in a relative sense within that model, but in the bigger picture, someone else might model the same system and get a very different number. So interestingly, several papers here talk about some standardized approaches to building models, and all of these happen to be product DSM models where different groups of students were compared or directed or not and how they built the models. And so there are some interesting possibilities to continue this line of research about how do we build, what's a systematic approach, is there some do's and don'ts to keep in mind. Another interesting development has been how do we create DSMs automatically, much more quickly. And this is very nice because this building a DSM is a big, challenging step for a lot of people. But what if you can just create it instantaneously? And so there's the question of how good is it when you do that? How good is your source material?
So the vision here to solve that, we reduce the product development lead time.
That's very attractive. It allows you to get on to the more interesting uses of DSM and analyses. So the folks from Lattice and also researchers from Harvard Business School had taken similar but not the same approaches to building DSMs from source code to represent software architectures. So that was an interesting approach. Some have used unified modeling language, UML models, which is a systems engineering oriented modeling language. Function behavior state models. Here's another example of that. So these are some existing ones. A question that has been in front of us for a few years, we've had some discussion about it. CAD models, building information models. These hold a lot of potential, but we need to see some real use of this. Can we take a bunch of CAD component models and extract from them the DSM that represents that overall product? We've talked about it, but haven't seen it yet. So we want to be able to do that. That would help with some of this consistency problem that we talked about in building product DSMs. Building information models, big possibility for the construction industry, where they have the building architecture in a database. Could we extract that and look at it as a DSM? So there are other possibilities, but these are a few in terms of building DSMs. So what about when the DSMs get big? And this has happened prominently in the software DSM area. The Lattice tool is one of the good ones at managing very large DSMs. And as you start decomposing, getting more and more elements, you can't even look at it all at once on a computer screen. There are some 10,000 by 10,000 DSMs that were created from software architectures. So it's nice to be able to kind of expand and collapse rows and columns, look at different areas, use different shading to show the different areas in such a large DSM. But kind of getting back to building DSMs, when we have very large models, distributed versus centralized model building. Some modelers take the approach of one person or a small group is going to build the DSM model. But especially if you're modeling a complex design process, like for an automobile or an airplane or a spacecraft, a naval ship, no one person really knows this entire process, at least not really. They may have it at a high level, but they don't really know the ins and outs, the details. And so you really, if you want to have a rich, accurate model, you need to go to the subject matter experts in each of those various activities. But none of them has the whole big picture either. And so you need a way to collect distributed inputs, small inputs from many people rather than just large inputs from a few people, and put all those pieces together, integrate them to make a model. But that requires more than just a DSM spreadsheet. It'd be too much work. So really some kind of web-based system to kind of go out and collect that information, automate the email reminders that are needed to all these subject matter experts. And then once they submit, check automatically to make sure that it integrates, that it matches. When I say I need something from someone, that someone agrees that they provide it. I've found that in most organizations where I've asked those types of questions, more than half the people don't agree. Most people don't really understand that set of relationships between what they give and what they get. And just figuring that out is a huge value to that organization, a huge benefit, just getting them to be on the same page with who does what. So data import and export, if we have DSM tools, we'd like to be able to get a lot of data into them quickly, and then we'd like to be able to take the results and feed them into other tools like Microsoft Project or something like that, that is used to manage day-to-day work. So some of this model automation I just mentioned, but also versioning and configuration management. Usually there won't be just one DSM model. You may start with one baseline model, but you'll want to start playing with it. You'll want to start modifying it. You'll have a what if this, what if that, different scenarios. So quickly you'll find you want multiple versions of your model. And then if you're really good, as you get more information, you'll go in and start changing and improving your model, making it even better. But you may want to save your older versions of the model to see how this is happening, because you might find you want to go back to one of those older versions at some point. And so how do you maintain version control? How do you maintain configuration control? The valuable DSM model is going to be a living model, an evolving model. And so it's like any complex product design, you need the same type of configuration and version control. How do you decide who does and does not see the model, change the model? Security, permission, this type of thing. As DSM models start to capture and contain more and more valuable information, it would become more and more problematic for the wrong person to access it or to go in and just start changing it. And so you would want to think about how would you protect the information in a valuable model. And then this idea of a local neighborhood, maybe these permissions are granted only to change or see parts of the model, not all of it. Different parts of the organization, different teams, different people get to see some part of it, but not the other part of it. Or they get to change their part of it, but not everyone else's part of it. And then how do you support negotiations where different parts of the model getting changed by different parts of the organization? You want them to do that in agreement with all the other parts that they touch. So you don't want them just changing things unilaterally when they have implications for other areas in the organization. You want them to negotiate those changes and agree to them. And so is there some way to support that and automate that? Hi, welcome, Steve. Glad you made it. So this one's about 20 years old, but this is from an old tool from Boeing, where they were supporting this hierarchical process modeling, taking a high-level process model, breaking it down into pieces where the pieces were maybe built by different parts of the organization, and then they could integrate and analyze all of this at the lower level, which has a lot of benefits to it. So displaying DSMs, what possibilities are there? Almost endless. These are just a few examples of different DSM representations, sometimes using numbers, colors, shading, symbols, taking additional regions outside the DSM to represent connections to other areas, and then putting those together. These are just a few possibilities. So what else might we do with displaying DSMs? And here's a screenshot from the Lattice tool where you can see some of the shading choices they've chosen. And it doesn't show it on this slide, but it's actually possible to collapse some of these larger squares into a single cell and then expand them back into the full part of the matrix again. And so this is a nice capability to have when you've got a large DSM. Here's another example of display where more than one number or symbol could go in each cell, and where it's located in the cell might indicate what type of relationship we're talking about. So this particular one is showing different types of relationships among components in a product, like spatial or energy or material type relationships, and their strength, which is shown by the number and by the shading. And so these are a few more possibilities. Sometimes we do, sometimes we don't show the background grid. So if there's a big sparse area in the DSM, sometimes it's visually appealing to just not show it. It just kind of crowds things. Similarly, I see some DSMs with zeros where there is no relationship, but it's actually useful, I think, to just leave it blank. It's, again, a little easier to see the real relationships in those cases. Here's another interesting DSM display where there are little bar graphs in each of the off-diagonal cells. Instead of a number, in this case, maybe two numbers multiplied together, it would be some decimal number like 0.18 or something. That's really hard to read when you get a whole table of those things. But here, the bar graphs where different size graphs actually have different shading as well. It's much easier to see where the bigger, important, stronger relationships are, even in a very dense, crowded DSM. So that's interesting. This one gets much harder to read, but this is an attempt to do a three-dimensional DSM with multiple layers all at once. So here we're looking at multiple variants of a product all at once. And each variant is another layer in the DSM. And the intention is to try to see common elements across different variants of the product, common components, and then distinguish the different components or interfaces. So again, I'm not sure that this one is as easy to read and understand yet as we'd like, but it's an idea that sometimes we need to stack layers of DSMs. And maybe there's ways to look at that. This one actually you can rotate in 3 dimensions to see different aspects at once, because it's hard to see all of it at once. So how do we design DSMs? So we talk about design thinking when we apply it to products, but maybe this idea can go to DSMs as well. And just thinking about how do we convey the message for any particular representation. Something else to think about here is sometimes, like I mentioned earlier, DSM is not the best way to convey every message. And so how do you toggle back and forth to other views, whether it's a graph, directed graph, whether it's a Gantt chart, whether it's some other type of representation, depending on your audience, depending on the question you're trying to answer, some other view might be better than DSM. And then, of course, the question is, when is DSM the best view? When should we want to make sure and use it rather than something else? So how do we fit our views with whatever purpose or concern or decision we're trying to support or use case that we have in mind is a good question for further research. So let's talk a little about analysis. What opportunities are there for analysis? Well, start with clustering. Clustering is one of those things we talk about a lot with DSM. You see it in a lot of DSM papers. When you dig a little below the surface, though, you'll find that there are many different clustering algorithms, many possibilities here. There not only are many algorithms, but there are many objective functions that we might choose. So there's a lot of question out there, I think a lot of opportunity to provide some good systematic guidance to people about which method, which objective functions work best for different types of applications and problems. So the algorithms are really just the how, and a lot of that's very automated now. You know, there's different optimization tools you can easily buy off the shelf. There's genetic algorithms, there's all sorts of optimization approaches, meta-heuristics, and so on. The bigger challenge from the how, I think, is the why, deciding what your goal is with this clustering, what's the real objective function, because any tool, any algorithm will, you know, automatically optimize whatever you tell it to. But how do you know you're telling it the right thing? How do you know that that's really the best answer just because it says so? And so what's the real objective? A lot of this depends on what factors you've included in the model. So basic clustering, you've just got binary elements with a yes-no relationship among them. But what if the relationships have different strengths, different degrees? What if the elements themselves have different amounts of importance? So all of this might have a bearing on how you assign them to clusters. But many clustering algorithms don't account for that type of information. And if you say we do want to account for that type of information, then the question is, okay, how do you best do that in a clustering algorithm? So these are opportunities, again, to take this very common, widespread approach called clustering and actually give some specific guidance on how to do it, why we do it, what we include or don't, depending on what we're trying to solve or answer. Sometimes there's not just one optimum answer. Sometimes there are multiple objectives, multi-criteria optimization is needed. So then what are the trade-offs involved? Should the clusters overlap or not? few clustering algorithms allow for overlapping clusters. Many times this is a manual second step. People go in and say, well, I think these clusters should overlap. But a lot of the clustering algorithms, especially ones you can just find on the internet, will not allow this type of overlapping. So with clustering, another thing that would be great to automate or facilitate is you've got multiple solutions that you want to compare and contrast. You want to see, okay, this algorithm, this objective function suggests this set of clusters. This other one suggests another set of clusters. How are they different? Why are they different? And how can I quickly compare? How can I toggle back and forth? How can I manually drag and drop to change and see immediately what the implication is? Do things get better? Do things get worse? This would be the ideal type of clustering tool, clustering environment, clustering workspace, or sandbox, we might even call it, where you can go and play and build and compare. And that's the tool that we're lacking right now. And so if we had some of our tool providers taking this in, that would be one big opportunity to provide a tool like that. Because there's tools where you can hit a button and get some clusters, but it's not really clear how, why, what is really going on there. And on the research side, as it says here on the bottom, there could be a nice literature review and guidance just on this idea of clustering that would be really valuable. So what about sequencing? So sequencing is how we typically begin to analyze process DSMs. And the good news is that there is kind of a first step that we use that gives a unique solution that identifies what we call strongly coupled components or coupled blocks along the diagonal in the DSM. However, it's really just a heuristic, because minimizing feedback loops is usually desirable, but it's not always the optimal answer. We can show cases where more rework is better. And so this is a nice first step, a nice starting point, but you don't always know the real answer, because this is just a heuristic. Remember, the real goal is not just minimize rework loops or feedback loops. The real goal is to try to reduce process time and cost while getting high quality. And so those are the real goals, and we want to be careful about prematurely backing off and optimizing something besides those real goals, like minimize number of feedback loops. So this multi-objective time, cost, and performance or quality set of trade-offs is again something that we need to facilitate with a tool that lets us play, compare, examine different options, different possibilities. One of the challenges here after the sequencing step is, what do we do with these coupled blocks once we find them? And so there are many proposed solutions out there, like tearing, looking at the eigenstructure of the submatrix, various approaches like that, and others. Which ones work best? Again, I think we have to go back to the real question about time, cost, and performance trade-offs. How do they affect those? What's the real objective here? What factors do we look at and compare here? Is it just a binary DSM? Or to what extent do we start accounting for all sorts of potential attributes of these activities and their relationships, like durations, rework possibilities, rework impacts, learning curves, resource availability? All of these things, of course, are extremely important, but basic DSM models just kind of gloss over a lot of those things. So depending on the situation, depending on the question, we need to go deeper than the top-level DSM models. Once again, the ideal tool here would give us this type of sandbox where we could play with the design space equivalent in the process world, call it the process space. So what do different arrangements or architectures of activities and relationships imply for project duration, cost, and performance? Other DSM analyses besides clustering and sequencing, there's many of these have been done, and there's more possibilities even. So one of the big ones has been change propagation. This one has been around for a while in terms of especially product DSMs. If you change one component that's related to other components, you can see the direct change effects, but then indirectly, how much further might these changes propagate onto other components? Sometimes in Britain, they call them knock-on effects. So this idea of indirect engineering change implications. Others have used social network analysis methods and algorithms and started to apply those to DSM. I think that's a natural symbiosis there. I think a challenge, something where we need more work, is what I have called here scale-free metrics. So I mentioned earlier with building DSMs that depending on what type of DSM you build, how far down you decompose the DSM, whether you represent your product as a 10 by 10 DSM or a 100 by 100 DSM. If you proceed to calculate metrics about the product, like amount of modularity or something like that, the answer you get from the 10 by 10 DSM is often very different than the answer you get from the 100 by 100 DSM. So is there such a thing as a modularity metric where you would get the same answer regardless of the scale you went to with the model? That's a challenge. Same in the world of processes. Are you going to get a similar project duration estimate from a 10 by 10 model of the process as you are from a 100 by 100 model of the process? In theory, you should. It's the same process. So the idea here is the models we make, the metrics we calculate from them, shouldn't be so dependent on our modeling decisions, ideally. So how can we get more towards metrics that are going to give us what we expect from different size or richness of models? That's a challenge. So product DSMs and organization DSMs are often snapshots, static pictures in time of how the product looked or how the organization looked at that time. How might those evolve over time? I think there's a lot of opportunities to look at product evolution, organization evolution with multiple DSMs at different points in time. And this could be done for process DSMs as well, because the activities we plan to do, think we're going to do today, probably aren't exactly the same ones we're actually going to do or think we're going to do a month or two later. And so it would be interesting to look at those as they evolve as well. So some work has already begun with architectural evolution, especially software products, because these are like the fruit flies in biology. Software changes very quickly, and so it's easy to compare multiple generations and see how they're different. Product DSMs for hardware, this it would be a slower process, but I think is also interesting to see how those would change. So you see some other potential analyses listed here. I think there are more that we could put on this list. We've got design rules, which are Baldwin and Clark's term for things you should or should not do in the design of a product. I've seen this applied mostly so far to software. How would it apply in hardware? That would be an interesting opportunity. How do we measure model improvement? Can we measure how good our model is? Does it give us 50% accuracy, 80%, accuracy, 90%, 95%? What confidence level does it give us? And then if we start adding more information to the model, making it richer, making it more accurate, how much better does the model get? How much closer to reality does it get? And a reason we might want to know this is because it'd be nice to kind of know the 80-20 rule for modeling. How much do I need to do in my model to get 80% of the final answer? We know people who just love to build models, and they'll keep modeling and building till they're like 99%. But in industry, that's not always practical. Sometimes we just want the quick 80% solution from a rough model. Other times we need a high fidelity model with really high accuracy and precision and confidence level, and we're willing to invest in that. So how do we know which type of model would fit which situation? How good is our model? And how much return on investment of additional effort would we get by improving a model? So those are some key questions that they're still out there. So this is an area that is especially interesting to me personally, although I haven't done much work in it over the last 7 or 8 years. But this was something I worked on with a Technical University of Munich PhD student quite a while back, Victor Leverdy. And this was on adaptive processes. This was looking at DSMs that had conditional or contingent relationships in them. So this was a model of a process where we didn't know that we wanted to do or would do all of the activities in the process. We said, depending on how things are, when we get to a certain step in the process, we may go one path or we may go another path. And so this process has really more than twice as many activities in it as you would probably expect to do. But what we did was, instead of assuming we knew everything ahead of time, which is an assumption in most process models and even project plans, it's actually a pretty dangerous assumption. Very few projects, especially complex engineering projects, really know all the tasks they need to do at the beginning. And so, and especially what order to do them in and what their results will be ahead of time, those are big assumptions. So this particular model said, we're just going to give some simple rules that when you get to a position in the project, you decide which next path to take based on where things are in the project in terms of cost, duration, and technical performance. So accounting for all three of those. So it was really what we call a complex adaptive system, allowing the project to self-organize, allowing the process path to kind of emerge rather than be prescribed in a plan ahead of time. And this was interesting because we could look at the result of thousands of simulations, and it's hard to read it here on this DSM, but on the diagonal we have the number of times that each activity was actually executed out of 4,000 simulation runs. And so I've highlighted a few interesting ones here. We have an activity that was executed over 16,000 times. So on average, more than 4 times per simulation run. In other words, it was reworked a lot. It was iterated a lot till they got it right. Then we have a couple other activities here. One, for example, was only executed 20 times out of this 4,000 simulation runs. Very rarely was it the best next activity to choose to do in the project. So this was reported. We discussed some potential implications, but I think it'd be interesting to further explore this. I mean, does the activity that's only chosen 20 times out of 4,000, should it just go away? Should the tools that we've spent money on to do that activity, was that a bad investment? Well, maybe. However, even though it was rare, 20 times out of 4,000, that activity was the highest expected value next thing to choose to do. And so maybe we can start to look at this kind of like buying insurance. And the question is, how much do you need? What should your deductible be? What's your premium going to be? We start thinking about process improvement in terms of, okay, there's a lot of potential things we could change. There's some just-in-case activities we may want to include in our development process. How much should we be willing to pay or spend for those types of activities? An approach like lean would say you need to go cut out the non-value adding activities. The problem is that sometimes the activity adds value and sometimes it doesn't. Obviously, if you don't need it on a particular case, then it didn't add value. But this is kind of like the person who says, I don't need insurance because my house didn't burn down last week. And yet, when there's a lot of cost pressure in industry, you don't have the ability to afford as much insurance as you might really like to have. So how do you decide? How do you choose where to buy insurance, where to hedge yourself, where to buy options at the right price in your process? These are a lot of interesting questions that I think DSM analysis could really facilitate and support. Final thing here, we also had numbers off the diagonal, not shown here, for how many times particular paths were chosen, including rework loops. And so interestingly, rather than using probability of input as rather than using probability of rework as an input to this type of model, a lot of DSM simulations have used probability of rework, but the question is, how do you know that probability ahead of time? Well, we ask as experts, we make estimates, that's great, but it's still a problematic number to put into a model. This model, the frequency of rework was an output rather than an input. It would tell us how many times particular rework loops were the best value-adding choice of the next thing to do, and therefore get selected. So that was interesting. We could see rework as an output of the model rather than having to assume it as some kind of input. Other process DSM opportunities. I was talking at the break about applying DSM to manufacturing processes. And I think most DSM process models have been applied to projects, especially product development, product design projects. What possibilities are there to apply them to repetitive manufacturing processes, where the goal is not to just do each activity once, but to repeatedly do a set of activities with a number of inputs? And we're interested in things like flow rates and throughput times and cycle times rather than just project duration or something like that. So I have not yet seen applications of process DSMs to these repetitive manufacturing processes or even other repetitive business processes like taking orders or something like that. I think it'd be interesting to have some tighter integration with risk management. So we can look at rework probabilities, rework impacts, rework risks, but do we just take that as an output and live with it? Maybe we can proactively do something to reduce the probability of certain reworks. Maybe we can make certain activities more robust to changes so that they're less likely to be affected by an engineering change or design change. Well, those types of investments have a cost. What's the benefit in terms of improved expected project duration or cost or anything like that? So I think there'd be possibilities to use DSM process models to look at some of these investments in risk reduction versus the return in terms of expected project improvement. Of course, I think more case studies of applying DSMs to projects would be really interesting. DSMs as a whole seem to have made great inroads in the product design, systems engineering, even organization design areas. It's ironic to me that most DSM research is focused more on process DSMs, but there has been much less traction, much less penetration into the project management community with DSM. Even though there have been some notable cases of it, you won't find DSM in the project management body of knowledge, PMBOK guide. You won't find it in most project management textbooks. I know some of the authors of those textbooks, and they say, well, we're just waiting on some real proof, some real simple explanations of cases and that sort of thing that we could include in such a book. So I think that would be great to get some more of that. Types of things that might get presented not just at a DSM conference, but at a project management conference using DSMs. I think here in Brazil with the Journal of Modern Project Management is probably the best example of a project management audience that's really interested in DSM. So I think you're at the forefront, Zosimo, of helping with that connection. Even much more so than in the US and Europe, where project management's largely disconnected from the world of DSM. So other DSM opportunities, and tell me when my time is up here. Do I have till 11 or? Okay. So looking at not just product, process, organization, DSMs, but like we saw earlier today from Bosch, what would a DSM of the various tools used and their input-output relationships of information, what might that look like? There have been a few of these, but there could be more. We could look at other resources required by activities as well as the tools they use. Could look at facilities, test labs. We could look at other types of resources. What are the goals and requirements for a project or for a system? So requirements are related to each other. Sometimes achieving one requirement makes it harder to achieve another requirement. Sometimes these are competing requirements. It could be a negative sign in the DSM to represent a relationship between two competing requirements, or a positive sign to represent making one requirement makes it easier to get another requirement. Maybe we could use numbers to show strengths or degrees of these relationships. So there have been one or two of these out there in the literature, but very few compared to product, process, and organization. And then what other types of domains or systems might we apply DSMs to? The paper mentions several other interesting ones. So I showed that diagram at the beginning of how people in science see each other. That would be another. What other types of networks, what other types of relationships are there out there that could benefit from looking at them this way? So DMM, MDM, we start taking more than one of these systems at a time and relating them, mapping them, comparing them. So product, process, organization, some of these domain mapping matrices are pretty common. So this one right here, process organization, this is used often in project management. So they're using DSMs a lot without necessarily calling them that. It's called a RACI chart sometimes. Who's responsible, who's accountable, and so on. Assigning people to tasks in the process. Many of you have worked with many of these types of DSMs and DMMs and combinations as MDMs. What are some of the things we need to know here? What are some of the opportunities? Well, there have been a lot of examples of these MDMs, but I think we still need more about what can we learn from these models that we can't learn from individual DSMs or DMMs. What's the real benefit? What's the added value of putting more than one of these models together? I think that's implicit in some of the cases, but I think it might be good to make it more explicit. Talk about that more directly. How are these useful to managers? What type of questions can these answer for managers? Why would managers want more of this stuff? Those are good questions that I think our papers should try to answer. And I think another interesting question for DSMs and all of these is, as I talked before about how can we measure how good or how accurate our models are, it'd be interesting to compare a model built at the very beginning of a project with the models we typically build are kind of midstream in projects. Once we have some information about the work and the product and the organization, we like to drop in and model that. But what about the genesis of the project when a lot of that stuff is really fuzzy? The fuzzy front end, as it's sometimes called. How good of a model of any of these areas can you really build at that point? And then as you progress through a project, how quickly, how easily can you make your model better, more accurate? And how would you know? And this might help managers decide, okay, how much should I try to focus on DSM modeling at the very beginning of the project when I'm planning it out? And then how much should I defer? How much should I wait and try to do later? And what are the trade-offs either way? What would I really want to know at the beginning of the project that if I waited, it might be too late to change? Or what is it that I just couldn't know at the beginning and it would be a waste of time to pretend I've got an accurate model? Those would be some interesting questions. I think one of our big buzzwords these days in the business school is big data, data analytics. We hear a lot about this, and there are certainly a lot of jobs becoming available. So we're focusing quite a bit on equipping our students to know how to do well in this environment. I think with DSM, there's a natural connection to big data. So if we can make that more explicit, I think there are opportunities there. Okay, I'm about finished. One final interesting thing from the paper was, since we looked at so many journal papers, we thought we'd just kind of compare and look at which journals have put out the most DSM papers. And you'll notice the majority here, the top ones, are mechanical engineering, engineering design, concurrent engineering areas. So and these are just journal papers, not conference papers. Next, we start getting to the engineering management and systems engineering, then another research and engineering design. And then we've got JMPM with only about 3 years worth of papers already up there in the middle of this pack. And so that's been a fast progression. Interestingly, we've got a Chinese journal. All the papers are only in Chinese. Maybe the abstract is in English sometimes. But a number of DSM papers appearing there. And a lot of recent interest over in China. I was over there a couple months ago, and they're especially interested in this from an engineering management standpoint. Then we start to see a variety of other journals after this point, not necessarily focused on one particular discipline. And this only goes down to journals that have 5 or more papers. There are, of course, many, many more journals that have 1 to 4 DSM papers in them. So 521 journal papers, in fact, as of about a year ago when this count was made. So I think that's great. Nice to have academic journal papers. Question here I put up, okay, how do we speak to practitioners? How can we get this message out to people in industry as well? And there are a number of DSM articles in practitioner-oriented outlets as well. That's great. I think we probably ought to put a little more focus on that if possible to get this message out. And these don't have to be long, involved papers. They can be pretty short, specific, how do you do one thing well type example papers. And this DSM survey I did was focused mainly on journal papers. So we've got now 18 years of DSM conference papers and presentations. So it would be an interesting opportunity for some ambitious PhD student maybe to look at that literature and see, you know, many of those papers emerge later as journal papers. So it's not like the survey I did is completely ignoring what we do in the DSM conference. But unfortunately, there's a number of DSM conference papers and presentations over the years that never went further than that because their authors just didn't want to take the time, I guess, to try to get it published in a journal. So there's some interesting stuff back there in these 18 years of DSM conferences. And we don't want to reinvent the wheel. So it would be nice to kind of have a survey of that so we can see what's been done already and what remains to be done. So the conclusion here, some big opportunities. I've gone through a bunch of these in the presentation. I think knowledge management, using DSM as kind of the tip of the iceberg, the front-end user interface for people to access much more extensive knowledge about products, their components, their relationships, processes, tasks, flow relationships. I think there's a lot of possibilities in those metrics, scale-free metrics, effort versus model accuracy type metrics. A lot of opportunities there. What are the implications of these modules and cycles that we talk about on what we're really interested in, like quality, technical performance, duration, cost? Those are the things that really will resonate with managers when we can show those connections. What are some improved tools for building, manipulating, playing with, comparing DSMs? We've got some that are evolving, trying to get there, but we still got a lot of room for improvement. How do we guide managers and model builders with MDMs? What are big data applications? How do we cluster, and I should say sequence or do other analyses as well, considering multiple objectives at once, not just focusing on one thing prematurely. And then how do we get more of this great stuff into the world of project management? Those are some applications here. So with that, I don't know that we have a lot of official question time, but I'm always happy to take questions or talk with anyone later about any questions you have. So thank you very much.